Hi, my name is Professor James. Welcome to this journey through space. Today we are going to study the chapter, which is Finite Element Analysis, FEA, in aircraft structures. In this chapter, we'll explore the importance of FEA in understanding the behavior of aircraft structures under different loading conditions. We will also discuss the role of stress-strain analysis, modal analysis, and fatigue analysis in predicting the performance and durability of aircraft components. Let's dive into the world of FEA, the tool that allows engineers to simulate the response of complex structures like wings, fuselage, and landing gear under real-world conditions. What is finite element analysis, FEA? Finite element analysis, FEA, is a numerical method used to solve engineering problems by subdividing complex structures into smaller, manageable parts known as finite elements. In FEA, the continuous structure is discretized into elements, each represented by a set of equations. These equations describe how the structure behaves under various forces. FEA is used to analyze everything from aerodynamic forces on wings to structural stresses in fuselages, allowing engineers to predict how the structure will perform without physical testing. The method is essential for optimizing weight-to-strength ratios, ensuring that aircraft structures are as strong as necessary without being unnecessarily heavy. By simulating the behavior of the structure, engineers can predict failure modes, identify weak points, and optimize designs to meet stringent safety and performance requirements. The primary advantage of FEA is its ability to simulate complex geometries and load conditions that are difficult or impossible to analyze analytically. Yushin Nei. Applications of FEA in aerospace. FEA plays a crucial role in the aerospace industry, where structural integrity, aerodynamic performance, and safety are paramount. Structural analysis of components like wings, fuselages, and landing gear helps ensure that they can withstand the various forces experienced during flight, including aerodynamic loads and impact forces. Optimization of weight-to-strength ratios is critical in aircraft design, where every kilogram matters for fuel efficiency and overall performance. FEA also helps predict failure modes, such as cracking, fatigue, and buckling, which is essential for the safety certification of aircraft components. Certification and compliance verification are key in ensuring that all components meet industry standards and regulations, like those set by FAR CS25 for large aircraft. Without FEA, physical testing would be required for every design iteration, making it both time-consuming and expensive, especially for complex structures. Stress-strain fundamentals. The foundation of structural analysis relies on understanding the relationship between applied forces and the resulting material deformation. Stress is defined as the internal resistance of a material to deformation, and it comes in several forms: normal stress, tensile, compressive, and shear stress. The von Mises stress is a critical factor in predicting failure, as it combines multiple stress components into a single value that indicates when the material will fail. Strain represents the amount of deformation per unit length in response to stress, with materials exhibiting elastic, reversible, or plastic permanent deformation. The stress-strain curve for materials like aerospace, aluminum alloys, shows how they behave under different loads, indicating the elastic and plastic regions and the point at which failure occurs. Understanding these fundamentals is crucial for designing components that can safely withstand the stresses encountered during flight, such as in wings, fuselages, and landing gear. Material properties for aerospace. FEA. Material selection is a key factor in the accuracy of FEA results, as different materials have distinct properties that influence their behavior under stress. Aluminum alloys, especially the 2XXX and 7XXX series, are commonly used in aerospace due to their high strength-to-weight ratio and good fatigue resistance. Composites, such as carbon fiber reinforced polymer, CFRP, and glass fiber reinforced polymer, GFRP, have anisotropic properties, meaning their behavior depends on the direction of the load. Titanium alloys like Ti6Al4V are used in high-stress components due to their excellent corrosion resistance and high-temperature capabilities. Specialized steels are used in landing gear and other high-stress parts for their high hardness and toughness, ensuring durability under extreme loads. Proper material selection based on temperature-dependent properties and real-world performance data ensures that FEA simulations accurately reflect the behavior of components in actual operating conditions. Meshing techniques. In FEA, the meshing process is essential for dividing a complex structure into smaller elements that can be analyzed. Meshing involves discretizing the structure into small elements, with each element representing a small portion of the overall structure. A fine mesh is used in areas of high stress or complex geometry, while a coarse mesh can be used in regions with less critical behavior. Mesh density is critical. If the mesh is too coarse, the simulation will yield inaccurate results, but a fine mesh requires more computational resources. Mesh quality metrics, like aspect ratio, ideal 3.1, and skewness, preferably 0.7, are used to ensure accurate results and efficient computation. Mesh refinement studies help engineers verify the accuracy of their simulations and ensure that the solution is independent of the mesh discretization. Load cases in aerospace structures. Load cases represent the different types of forces and conditions that aerospace structures must withstand during their operation. Limit loads represent the maximum expected loads during regular flight operations, while ultimate loads are typically limit loads multiplied by a safety factor. Combined loading scenarios involve the simultaneous application of multiple load types, such as aerodynamic loads, gravity, and inertial forces. Compliance with aerodynamic load distribution, such as pressure distribution from CFD, computational fluid dynamics, is crucial for simulating real-world flight conditions. Regulatory requirements such as FAR CS23 for small aircraft and FAR CS25 for large aircraft mandate specific load case simulations to ensure structural safety. Proper application of loads ensures that FEA results accurately reflect the performance of aircraft structures under realistic operating conditions. Modal analysis, vibrations in aircraft. Modal analysis is used to determine the natural frequencies and mode shapes of aircraft structures to predict their response to dynamic loading. Eigenvalues represent the natural frequencies of the structure, while eigenvectors describe the corresponding mode shapes of vibration. These analyses help predict how structures will respond to dynamic loading, such as turbulence, engine vibrations, or control surface deflections. Identifying potential resonance conditions is essential for preventing flutter, a potentially catastrophic aeroelastic phenomenon that can occur at certain vibration frequencies. Modal analysis is crucial for preventing structural damage due to dynamic forces, ensuring the structural integrity of wings, fuselage, and other critical components. Visualizing the first few vibration modes allows engineers to identify weak spots in the design and improve its dynamic performance. Fatigue analysis and safety margins. Fatigue analysis is used to predict how components will perform under repeated loading conditions, a crucial factor in ensuring the longevity and safety of aerospace structures. Aircraft structures are subject to cyclic loading, including repeated takeoffs, landings, and turbulence. Over time, this can lead to fatigue damage. By analyzing the stress ranges and load spectra, engineers can identify critical locations in components that are most susceptible to fatigue. SN curves, also called Wöhler curves, are used to predict the number of cycles to failure based on the stress levels. Cumulative damage is calculated using Miner's rule, which helps determine when parts will need to be inspected or replaced.